I want to take a little bit of time and tell you about this new program that we started and focus really on the component that's the sustainability component and how I think the right way to work sustainability as a topic into an engineering curriculum. And first and foremost, I think that the important thing is not to do it in place of the disciplinary depth necessary to be a good engineer. It's not in place of what you're taking. Sustainability as a subject area is essentially what you all do in engineering anyway. It's a systems analysis. It's sort of system-wide life cycle thinking about the products and processes you're designing. So it's a context in which you can teach all the curriculum that's normally in an engineering program. And I'll sort of show you that with some examples about how we do that in problem-based learning in our curriculum at JMU. And I like to think of an engineering curriculum that we always have these arguments about breadth versus depth in an engineering curriculum. Yeah.
Just a note, I think about half the class are engineers and half are from the science.
Oh, that's cool. Well, yeah, you can substitute those words interchangeably. Science and engineering are, two sides of the same coin. So, so we're in good shape. I kind of always have these discussions with people about depth versus breadth in curriculum, and faculty in the room will understand this and know that this is always the argument that's going on. How broad do you go? Do you sacrifice depth in a subject in order to get really good broad context, or do you really get narrowed and focused and give you lots of depth, but then you don't have any context to use that information? And I kind of want to turn that argument around. I don't think we should be talking breadth versus depth, because then you kind of think of rectangles and the area under a rectangle. At least that's what happens to me, So, if it's really broad and not very deep, it's got a small area, and that's not good. If it's really, really narrow and really, really high, doesn't have much area. So there's some, square in there that has the optimum area. But that makes it sound like a trade-off. I think the better way to think about the way to introduce a subject like sustainability in an engineering or science curriculum is to think of a T-shaped curriculum. And I think T-shaped curricula are really what we're talking about here, where you have your disciplinary depth in some area. If you're a chemistry major or a mechanical engineering major or a physics major or a biology major, you'll have specific disciplinary depth, but everybody ought to have that breadth component, the top of the T, that connects you together so you can talk to the other disciplines. Because it's okay to be a disciplinary expert, but in today's problems, as you'll see, they're so interdisciplinary, you have to be able to speak the language of other scientists and engineers, or else you're never going to work in interdisciplinary teams to solve any real problems. So that's kind of where we're going. So I gave you the whole talk in 3 minutes, so we could just stop now, or I can finish the presentation, whichever you prefer. So when we built this new engineering degree at JMU, and this is sort of the context for the discussion, was the design of this. We really asked industry, government labs, National Academy of Engineering, graduate programs, since we were producing undergraduates, about what could you do if you had a blank sheet of paper and could start a new curriculum. How would you go about doing it? Well, industry really focused on 3 major things. They said, first of all, we need versatilists in our companies. For several reasons. The problems are interdisciplinary. We need people who understand how to learn. But most of the companies would, if you're a small company, they to hire 10 or 15 experts. They need somebody who can cover a broad range of things. And even the large companies, one of the GE executives said, I can't look an engineer when I hire them in the eye and tell them exactly what I'm going to have them doing 3 years from now. I know what their first assignment's going to be, but our business has changed so fast that I need them to be able to morph along with our company, or else I'm going to have to lay them off. So that versatility in self-learning was a really key component. So that was one thing. The second thing we really learned from talking to companies was practical ingenuity is really missing in a lot of bachelor degree programs. And this, I think, goes across science and engineering. And a lot of people leave undergraduate degrees having a lot of book knowledge and having not much practical skills. And the great example we heard from on this one was a company that was a construction firm. Said they hired an engineer with a master's degree in construction engineering, and they'd never been on a construction site one day in their life yet. And they assigned them the job of doing a piping system under a building in a crawl space. And they got their CAD out and they drew a beautiful pipe layout, minimum linear feet of pipe. They did all the optimization just right the way they're supposed to. Now, unfortunately, the valves ended up in places that no human could ever get to repair because of the way they laid it out. So that's one of those practical ingenuity things that comes from actually doing projects, not just studying them in a book. So that was the second big piece of advice we got. And then, sort of the reason for today, the third piece of information we got was everybody wanted us to focus on sustainability. And they wanted it for several different reasons. One was, and I have to sort of unpack this a little bit. So one of the reasons was when you talk to companies, what they really were after was not necessarily environmental engineers. They want people who understand sustainability from a systems point of view, who can think about a problem from cradle to grave, who when they're designing a product, they're designing this little widget, they don't think about just the widget, they're thinking about this in its whole life cycle, from all the materials that went into making it, all the way through to how we're going to get rid of it, disassemble it, and dispose of it at the end of its life cycle. And we got that for two different reasons, and I'm oversimplifying. There were a whole spectrum of reasons, but sort of represented by these two books. There's sort of the cradle-to-cradle argument. If you're familiar with that book, it kind of makes the moral imperative argument about why we should be leaving the planet in a better position than we got it as we enter our working lives. But just as many companies, interestingly enough, were kind of giving the greed to gold argument, which was, if my engineers are designing products that use less energy, use less materials, and generate less waste, the odds are pretty strong they just develop for me the cheapest alternative for what I was trying to do. So even if they don't have a moral imperative for a sustainable product, they saw a strong financial drive for why thinking in this life cycle kind of mode produces more financially sustainable solutions. So those are kind of the main reasons behind designing a new kind of degree. And while this was going on, the National Academy of Engineering was doing a study about the problems that engineers and scientists can attack over the next generation that are the sort of the big global scale problems that if we could do something about them would have a significant impact on mankind. And they did an international survey, and this is about two years ago or so, and they asked for these problems, and they developed a list of 14 problems that they call the grand challenges. And these are the problems that if engineering and science community can do something significant about these, we will have really changed mankind. And these are the big problems. Look, solar energy, providing clean water, carbon sequestration, the nitrogen cycle, cybersecurity, medicine, informatics. These are the big issues. There's a few seats if you want to come up and grab one, no problem. The point I want to make about these, provide clean access to clean water. What discipline in science or engineering does that? Right? There's no one, right? You need chemistry, you need biology, you need civil engineering, you need mechanical engineering, you need electrical engineering, you probably need industrial engineering. You need a bunch of different disciplines in order to crack one of these problems. So these are not disciplinary problems. So that's pretty indicative of the kind of problems you all will be dealing with when you get out in the workforce, is you'll be dealing with problems that are going to require you to form a team of 6, 7, 8, 9, 20, 30 people with different disciplinary backgrounds to solve a problem. So that's the background for designing a new degree program. Being engineers, we need design parameters. That's what we do. So we said, what are the design parameters in designing our new degree? Well, what we decided to do at JMU was build a single bachelor's degree in engineering. So every single student gets the same degree, Bachelor's of Science in Engineering. We do not break into mechanical, civil, electrical, chemical. Everybody gets the same degree. We wanted to keep the program small. This is an old slide. We wanted to have 50, 75 students per year. We actually are more like 120 students a year entering the program, but it's still small relative to most engineering programs. And the reason is you'll see it's a heavy design component, lots of design and build, so we really can't have large groups of students. Of course, the degree is designed to meet all the ABET accreditation standards so that it will be an ABET accredited degree program. That's the licensing accrediting body for engineering. Every student in our program is required to take the FE exam. If you're not familiar with this is the Fundamentals of Engineering exam. This is the exam a student would take upon finishing their bachelor's degree in engineering. You pass this exam, then you practice for 5 years, and then you can sit for what's called the PE, or Professional Engineering degree, or exam. And that's when you can actually be a licensed professional engineer. So every student in our program will take that exam before they graduate. So that helped us define the curriculum. And then being a traditional liberal arts university, James Madison, our curricula are 120 credit 4-year curricula. Most engineering programs at other schools are 130, 135 credits. They have more credits in them than the other degrees. Our challenge was to see if we could design an engineering degree that fit within that 120 credit size. And I strongly believed we could, and we have. So even though it's a single degree, the degree has to have a focus. So this is where the focus of sustainability sort of married with the idea of engineering design being our primary focus for the degree. Heavy, heavy design component, as you'll see. And systems analysis. Because when you talk to companies at the bachelor's level, when they're hiring an engineer or a scientist, they're looking for 2 or 3 things. They're looking for problem-solving skills, analysis skills, and design skills. That's really what a company looks for at the bachelor's level. If they need an expert, the odds are they're going to hire at the master's or PhD level. Most companies, when they hire somebody at the bachelor's level, are looking for those skills. Now, even at the upper level, and this is not a new phenomenon. When I finished my PhD in chemical engineering, my first job was with DuPont. The very first assignment DuPont gave me was a circuit design. Right? The right answer was not to go to my boss and say, excuse me, I'm a chemical engineer, I can't do that. You get hired as an engineer. That's it. You don't have a prefix in front of it. You pull out your old circuits book, you figure out the problem, and you solve it. That's your job. So what discipline you learned how to do this problem solving in at the bachelor's level really doesn't matter. So those are the program foci. And when I say design, I wanted to spend a minute sort of defining what I mean by that from an engineering design point of view, because everybody's definition of sustainability is different. If you ask everybody in this room, would get, this many answers of what they mean. So let me use a metaphor here. Let's say you're an engineer and you're designing a bridge. If you're going to design that bridge, I see 4 primary design criteria that make it a sustainable engineering design. The first of these is the technical design parameters, because clearly if you're going to build this bridge, if it doesn't stand up to the wind loads and the car loads and it falls down, it doesn't really matter if it's sustainable in any other way, does it? So if it doesn't first and foremost meet the technical requirements, it's not going to be a good design. Secondly, you're probably building this bridge on a budget and timeline. So you have clear financial requirements to make this a sustainable project. And this will come back up in my example in a moment. The third one is the more traditional definition of sustainability, and that's you're going to have environmental requirements for this project. You're putting concrete pilings in the river. You're probably disturbing indigenous species that exist in that river. You have to examine what you're really doing there. Maybe you're changing the flow dynamics so that the erosion on the shorelines is going to be different than it would have been before the bridge was built. So you have to do an analysis of all this and make sure that you're sustainable from an environmental point of view. So if you haven't met the technical, financial, and environmental sustainability requirements, of course this project isn't going to fly. Unfortunately, a lot of engineering designs stop right there. I mean, right at this point, without this 4th bar that we consider important in the sort of the holding up the design process, and that's the societal requirements of your designs. So let's use that bridge, keep going. Okay, you just connected 2 communities across a river that maybe weren't connected before. What does that mean from the societal point of view? Maybe they have different socioeconomic situations on both sides of this river. There's probably businesses that this traffic flow is going to change. Some businesses might get more business than they used to. Some might get less business than they used to because traffic patterns are different. This bridge maybe should carry more than just cars. Do you want people who don't have cars to be able to get to jobs on the other side of the river? So do you need bike lanes? Do you need walking lanes? Maybe it's just a cool design and it's going to become a tourist attraction. That might change the socioeconomic status of the community this bridge is sitting in. There's all kinds of things that have nothing to do with the technical design of that bridge that are probably really important to the people that live on both sides. Wouldn't it be nice if the engineer designing this bridge met with those communities and took those design requirements into consideration along with the technical, financial, and environmental design requirements? So until you've met all 4 of these, in our opinion, you haven't really developed a truly sustainable design. And what we're really talking about, if you think about it this way, is you're really not talking about sustainable products and processes anymore. You're really transcending to sustainable societies. Because that's really the ultimate goal of sustainability, is sustainable societies. We don't care if widgets are sustainable. We compare if our society is sustainable. We just happen to be, as scientists and engineers, designing the widgets. But the point is ultimately to feed that sustainable society vision. So that's what our definition is. Now today's talk isn't really to focus heavily on curriculum, but I had to put one slide in here for the faculty in the room, because when you start talking about doing all this in 120 credits, it's okay, how? So let me just talk about broad categories. I'm not going to talk about courses. So first and foremost, I think it's really imperative that an engineer have a very, very strong general education base. The days of, the engineer being in the back little Dilbert cube and never coming out to talk to a customer or anybody else in the company are long, long gone. An engineer, by definition, is a very social job. You're out talking to CEOs and chief financial officers and customers and government regulators and other engineers and the public and everybody. There used to be an old joke that said that you could tell an extroverted engineer from an introverted engineer because the extroverted engineer would look at your shoes rather than their own when they're talking to you. And unfortunately, that's the stereotype that's out there. And it's not true, though. I mean, the really successful engineering and science folks that I know that really transcend their sort of disciplinary job in a company are the ones who have the skills associated with a strong general education. So this has to be there. Our students are required to take the entire 41-credit general education curriculum at JMU. Some universities will let you out of a couple of the general education courses in order to get the quote-unquote important engineering courses into the curriculum. We require the entire general education sequence because I think it's that important. Course, you have to have the basic science and math of any engineer. You take calculus through 4 semesters. You do physics with lab for a couple semesters. You do chemistry with lab. You do biology or geology. So you have your basic sciences. You have to do that. You have all the engineering science courses you'd expect to see: statics, dynamics, thermo, heat transfer, strength of materials, go down the list. All of those things are in there that you'd see in any engineering curriculum. The only difference is you're not seeing them in a disciplinary context. Thermo is a great example. Mechanical engineering departments have thermo. Civil engineering departments have thermo. Chemical engineering departments have thermo. Last time I checked, the first and second law of thermo weren't different for chemical engineers versus civil engineers. So really they're learning the same thing. What's the difference? Well, a civil engineer might be learning it in the context of an HVAC system. Mechanical engineer might be learning it in the context of an internal combustion engine. Chemie might be learning it in context of a chemical plant. But you're really doing the same exact calculations because it's a thermo course. So why not teach one thermo course and cover examples from all those disciplines? So you need to cover all the same basic engineering science. Really, really important to understand business processes. So we've actually partnered with the School of Business and have the business faculty teaching a 2-course management and technology sequence for all the engineering students. And those 2 courses set you up to, if you're interested in, taking the business minor or staying a 5th year to do an MBA in combination with the engineering degree. Every company said that an engineer has to have understanding of the financial processes in a business. And then we have the focus sustainability parts of the curriculum. Sustainability is actually woven through all the engineering science classes and design classes, but we have Sustainability 1, Sustainability 2, and Systems Analysis, which are 3 courses that focus exclusively on the tools of sustainability, life cycle assessment, things like that, and some of the software packages associated with doing those. And then finally, a really, really, really heavy design component. Most engineering curricula that you see would have 1 semester or 2 semesters of capstone design in the senior year. We have 7 semesters of design. That's an 8, sorry. 7 semesters of design in our curriculum. Second semester, freshman year, you start in an intro course that's a 5-credit design course, 5-hour design course. And then you take Design 1, Design 2, Design 3, Design 4, Design 5, and Design 6 in your sophomore, junior, and senior year. So every single semester, you're designing and building something. All the design studios have machine shops attached. So you design and build every semester. And the reason for this is we just have weird brains. It's one thing to be in a statics course and learning that. It's another thing to be in your statics course with its lab, but also that semester you're designing and building a bike. So in the process of designing and building the bike, you're applying your statics and your CAD in a real project. So just 2 weeks ago, the sophomores spent their Design 1, Design 2 course designing and building a bike for a gentleman who has cerebral palsy who wants to ride bikes and he can't ride traditional bikes. So they spent the first semester interviewing him, doing physical measurements on him to see what he can do and can't do, and then doing CAD concepts of prototype bikes that would allow him to ride. And then second semester, they were in teams in the shop building the bikes. And then 2 weeks ago, we had a day where we went outside, all the bikes were set up. He came over, he rode them around to figure out what aspects of each prototype worked well. Next year, the students in Design 3 are going to take his ideas and combine them together now into a single bike design that he'll actually, we did this with a client a year ago, and that person this year rode it in a real race, in a 5K bike race, which is kind of cool to see him riding for the first time in a real race. So really heavy design problems. The problem, though, this is a word that some of the students might not know, pedagogy. This is a quote of mine. Content is the evil of learning. We focus too much on content when we teach, and the students in the room are probably all nodding their head, right? We have this syllabus, and we try to cram every content item on the syllabus in, and we're racing near the end of the semester as faculty to finish it. We get to that last day, and we go, covered it all, we're done. We did our job. You know, we need to ask the question, did you actually learn it, not did we cover it, right? And that really comes to the style of teaching and how you do it. And pedagogy is the technique of teaching. And the only way you're going to get all this content in a curriculum in 120 hours and focus on sustainability at the same time is to really change pedagogically what you're doing. And so this brings up one of my favorite quotes. I have two quotes in this talk that I really want to focus on. And this is a Socrates quote, so it shows it's not a new idea. Education is the kindling of a flame, not the filling of a vessel. And I think a lot of the times we focus way too much on the vessel filling part of this and not enough on the kindling part of this, because really, if you're going to be a lifelong learner, our job is to, more like a coach, to motivate you to do it on your own than it is to feed you information.